Hey everybody, and welcome back to Calc 3 Online. So the plan for today is start talking about a very important topic called conservative vector fields. And we're going to have two videos on this stuff. Really useful in a lot of applied settings. Tons of the sciences and whatnot use these things. And what I'm going to try to show you today is that really what's kind of summed up in this. And this is actually so true. I feel like I can relate to this big time. I vividly remember times where I spent something like half an hour trying to parameterize some sort of curve for some line integral or something. And then I realized the vector field was conservative. And if it's conservative, you're going to see today that there's like a really nice result that we can solve it much easier, and we don't even have to really parameterize it. So conservative fields are kind of what they sound like. They sort of conserve the thing, and the thing can be like energy or something like that, right? Like if you look at like this one, okay, very similar fields, but this one is actually conservative and this one's not. Basically, if you look at it and the easiest way is honestly to do a loop, okay? So if you take a loop around, what color is going to show up well on there? Green. And you say we're kind of going this way around the loop, okay? You can see as we go around, like, this, like think of it like a line integral here, like, but it's around a loop, right? So having this vector field in the background, this kind of is going to create some, positive amount. But then this part right here and this part right here, you see how they're kind of acting opposite one each other, and they're going to cancel each other out. And then there's chunks like this part right here and this part right here, which also sort of cancel each other out. And then you also got stuff like this vector and this vector, which cancel each other out. And so what's nice is for conservative fields, as you go around some like loop, okay, this is what's down here, line integrals are really easy because no matter actually what loop you take, the line integral will always just be 0, which is super handy. If you do a line integral around a loop here, all right, and it really doesn't matter. I mean, I drew kind of the same circle, but I could do that, anything like that. Don't even have to be circles, actually. I mean, they can literally just be some weird thing like that. It just has to be some sort of closed curve. No matter what, the way the vector field works, all the, here, if you move this way around the path, okay, here you've got these vectors that are always kind of working in the direction of the curve, right, the path that you're moving. And so you're sort of always, if you think of work, right, it would take less work to go around the path this way than it would to go around this way. It's always kind of easy to go around it this way. You are not going to have net zero work, right? Whereas here, the way the forces work, right, being opposite in spots and whatnot, you're going to get net zero work no matter actually what path you take around this thing. And physically, I think work is probably the easiest way to think of these things, but they really can be all sorts of different things. You can do this for like electric fields, and if you go be a chemical engineer, you're going to like see these there and stuff. But the idea is basically that the work done by a conservative force field, and that force is really broad, as it moves an object around a closed path is 0. Just basically conserves all that energy or force or whatever you want to call it. So this right here is actually a super nice result. And you can see why it would speed this up. Like, you haven't really seen line integrals where the parameterization is actually really hard, and that's because it's really hard and I can't really give it to you right now, but down the road you'll get somewhere it's really hard to parameterize it, but it turns out that if it's conservative, and there's a way that will test that, you can basically just ignore this and you can just like put down 0 because because it will be 0. So actually the next thing I want to talk about is kind of where the definition for conservative vector field comes from, and also this thing, the fundamental theorem for line integrals. And in math, anytime you see this word fundamental, it's going to be something really important, so you really want to know it. And it actually does all kind of go back to this. So this is, of course, the fundamental theorem of, whoops, I don't know why I put a W. Fundamental theorem of calculus. And, we really do mean just like Calc 1 there. And, we've been using this forever and it makes total sense. In the language of vectors, okay, which is, we're now doing vector calculus, like this thing right here, basically, right, acts as that nabla thing, but the gradient, right? The gradient is like this, vector, where you basically, if you do like gradient of f, it's just going to equal like the partial of f with respect to x, partial of f with respect to y, like however many components you have, it just keeps taking the partials, right? And what I want you to see here is there's actually a way to sort of tie this in to an integral, and you're going to get, if you look at this and this, it basically has the structure of the fundamental theorem of calculus. This is what we're actually going to call the fundamental theorem of line integrals, okay? But, so d dt of f of r of t, right? This is going to have to be a chain rule thing, right? And we're going to take the derivative of f, right? And then we have to multiply it by the derivative of, like, the inside components of, the r. Like, if r is 3D, it would look like this. So you would have partial of f with respect to x, and then chain rule, you're going to do, actually, it would only be dx, like proper derivative, ordinary derivative, dx dt, and then partial of f with respect to y now, dy dt, plus partial of f with respect to z, dz dt. This is just chain rule, right, like from chapter 14. But if you look at this thing, right, you can really actually think of it as a dot product. You could look at it as you have partial of f of x, partial of f of y, partial of f of z, and then you've got dx dt, dy dt, dz dt. So it actually has a structure of the gradient of f, right, of r of t, I guess. And then dotted with, I messed it up. It's supposed to be green. Let's do that again. So the gradient of f of r of t dotted with r prime of t, really dt. Well, no dt. Sorry, just r prime. So, so then, okay, if I take this thing, right, and you pop it in here, right, this and this are equal, put it in there, take an integral from a to b, dt, you get this, right? And this right here, just like the fundamental theorem of calculus, we can do a fundamental theorem of line integrals and say that this integral from a to b of this thing, right, that I just sort of did down here, is going to equal just f of r of b, right, minus f of r of a. And this is the fundamental theorem of line integrals, this equaling this. And this is where you can really see that a conservative vector field is going to have a zero line integral, because if the beginning and end points here, the a and b, is the same, then the curve we have is a loop, okay? And when we have this kind of curve, the line integral is 0. And so with this in mind and the fact that, this structure right here is just how we write integral over a curve, f dot dr, right? It's just this thing, sort of. It means that the line integral of a conservative vector field, it's called VF. And we saw the definition of this in a previous video. It was one where f equaled gradient of f, like lowercase f. That is the definition of, so this right here is the definition of this right here. So basically, if you can replace, this f with this gradient, all right, then, this little part in here would just change to this, right? And so for these conservative vector fields where the start and the endpoints are the same, then you can just do the computation of that line integral with simple subtraction, which is super, super nice, okay? That is the fundamental theorem of line integrals. Just kind of wanted to sum up on one slide all the nice things and talk a little bit more about one part that I guess I didn't say yet. So, so this line integral that we're used to simplifies to this only in a conservative vector field. Okay, that's really the definition. This part becomes this part. There is such a thing as a fundamental theorem of line integrals, and it's just basically saying that this integral right here is equal to f of r of b minus f of r of a. And that is specifically this f, not this f, lowercase f, not big f. We'll talk about that in a second. And if you can just do subtraction, right, you kind of should see that based on this, it should be clear that if the field is conservative, right, then the line integral is what we would call, the fancy word is path independent, right? Basically this picture, if all you're doing is you have these 2 points, right, and this field back here was conservative, then you should be able to go along curve 1, 2, or 3, or any of them, right? And you can just do subtraction of the endpoints to get the line integral, right? This is just another picture. Basically, if the field is conservative that you're over, you can kind of move that ball along this way or that way, and like you can think work or something. The work should be the same as you go here versus as you go here. Like if you're thinking like I always think of this problem as like a mountain or something. And if you've got like a conservative field, which represents like maybe the slope changes of the mountain, you can take the really long path forever and like switch back your way up. And the work to get up it is the same versus you could just like punch straight up it and it's going to be over quicker, but the work is a little harder. So it's kind of conserves the work, right? So that's like the idea. But basically, there's this nice result that you can take any path you want. That's nice. And the line integral on a closed loop in a vector field, super, 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 super nice, is 0. Don't be Jean-Luc Picard over here and spend forever trying to parameterize conservative vector fields. And then this one is something that I'm not going to say too much about right now, but if you've taken some physics, you might already know that word. What's really happening here is the vector field has 0 curl, and that's a formal math operation, actually. It's a measurement of something. So, basically, it's this. It basically means that the field is irrotational, and I'll talk about that. But this is this is kind of key to understanding some of the later stuff in this unit. So. That's kind of what's happening with conservative fields. They're really nice. They make a lot of things easier. Okay. All right. So one of the kind of things that I want to talk about is that a lot of times students will get a 0 from a line integral, and then they'll say it's path independent, or, well, they'll say it's conservative is what I want to say, but that is not true. So this is true, that if f is a conservative field, then the line integral around that closed curve is of like the gradient of f dot dr is going to equal 0. That is true, okay? But this is not like an if and only if statement. So if you get 0 from a line integral, don't think that f is conservative. If for some reason you can show that along all closed paths you get 0, then you can actually conclude that f is conservative, but there are infinitely many closed paths, so you can't really ever do that. So in practice, we don't compute this and hope for 0 and then conclude that. There's a way that we'll get this, and then we can jump to this, okay? So don't think you can go from here back. And, over here I was just going to draw, like, you would have to do, like, infinitely many closed paths. So, actually, I kind of messed up. So, yeah, we can do it this way. So you can do... So the point I'm talking about is, like, this point right here. Like, maybe those are my 2 points, but you'd have to check all the different paths that are closed loops that get you back to that point or something. And there's too many to check, so you can't really use this thing backwards. You can say if f is conservative, then that happens. And I thought this would be a good time to show you another notation that will actually keep showing up. So sometimes you'll see, and actually in my room I have it, an integral with a little circle like that. And I like this because this thing feels very much like how I think a lot of Calc 3 students feel. You guys are lucky because we're doing this much earlier than the last week of vector calculus class normally would be. But a lot of times your professor will just throw this symbol out there and just start talking about it like everyone knows it, but no one knows what it is. All it is just an integral with a little circle there is saying just think of it as an integral around a closed loop. That's what the little closed loop is trying to show you. It's just trying to tell you a little more info about the path that the line integral is on, that it's a closed path in space, like any of these ones are. So that's all. Don't overthink it. We will talk about, there's actually an extension of this for double integrals, and you might have an idea if you've got some good intuition what that would be, but this is just an integral around a closed path. That's all it is, okay? So the question becomes, how do we find these, how do we do this? How do we get a conservative, how do we check, I guess, if there is such a lowercase f that capital F over here could equal the gradient of? Because if we do that, right, remember then capital F is conservative, and that's going to be nice. So this becomes probably the place where I feel like you end up doing a lot of the work. But then if you do this, you save yourself all the time on, like, Fountain Leaf card, right? So let's get into it. So I'm basically going to show you how I would take this and try to find if f is going to equal some gradient of lowercase f. All right, so to start off, just notice that basically if f is going to equal the gradient of some scalar function f, then we need two things, right? We need 3 plus 2xy to equal f with respect to x, and we need x squared minus 3y squared to equal f with respect to y, right? So what we basically do first is we can take the integral of f with respect to x dx. So we're going to take the integral of 3 plus 2xy with respect to x, right? And in that case, we're going to get 3x plus 2x squared over 2, so actually we'll kill that 2. And then we got a y still. And then notice that there should be a plus like g of y term, right? Because g of y would be constant with respect to a dx integral, right? So if you took the derivative with respect to x, right, this term would go away. So that could be there. It's kind of like my constant of integration. It is my constant of integration. So this is like a contender for what lowercase f could be, right? So what we're going to do is we're going to kind of utilize that to help us. So next we're going to take so this right here is like f, question mark. So what I'm going to do is that f that I have right there, I'm going to take the derivative with respect to y. So I would get, the 3x would go away, so I get just x squared plus g prime of y. And then what we're doing is we're sort of going back up here, right? And we want f with respect to y to equal x squared minus 3y squared. So using that, we see g prime of y must be minus 3y squared. And so then we can utilize that knowledge to actually fill in g of y, right, using an integral. So it's kind of just like a fun back and forth with integrals and derivatives, basically. But so now what I'll do is I'll take the integral of g prime of y, this time with respect to y, right? And so I would get minus 3y cubed over 3, so just minus y cubed, and then plus some sort of constant of integration. And so this thing is my g of y, right? And so now I can, as just like one last step, I can kind of go here and here, right? And I have my g of y. And so I can pop in that, and I can get f of x comma y equals 3x plus x squared y minus y cubed plus some sort of constant. So this thing, right, if you literally do the partial with respect to x, right, you'll get that. And if you do the partial with respect to y, you'll get that. This actually is, we really just solved a partial differential equation. Solving these kind of differential equations is, if you take DivEQ next year, we're going to do this kind of problem. This is like a very classic kind of technique to solve a differential equation. So just a little fact there for you. But this would be it. So this is my f of xy that I could now use as lowercase f here. The gradient of that equals f. So capital F is conservative. So this is the same capital F from before. And so now I just want to show you how quick it is to solve something like this if we know it's conservative. All right, so we know it's conservative. So we know that the line integral over a curve of capital F dot dr can really equal basically the line integral over a curve, and then just swap out capital F for gradient of lowercase f dot dr. And to do that, I'm just going to use that fundamental theorem of line integrals, okay? And so what this is going to look like is I'm basically just going to have to do, that integral is just going to equal f of r of b minus f of r of a, okay? So that's basically all I'm going to have to do, subtraction. So first we got to get r of b and r of b and r of a. And so let's do that. So r of b equals e to the pi sine pi, then e to the pi cosine pi, which would equal, let's see, so that'll be 0 here, and then cosine pi is -1, so minus e to the pi. And then r of a would equal, let's see, e to the 0 sine 0, e to the 0 cosine 0, which is going to equal just 0 and 1, which is nice. And so then I just have to do basically f of 0 minus e to the pi, and then minus f of 0, 1, okay? And I think I'm just going to hop down here. And so then you just are using this f, okay? And so you literally just go and plug in that. And so maybe I'll just down here, I'll just go and plug it in. All right, so I think that's all plugged in. So this is just using lowercase f, plugging in 0 minus e to the pi, plugging in, this is my f of 0, 1. And so you crank that all out, and you should get e to the 3 pi plus 1. That's it. So that's pretty much it for this video. That's all I kind of wanted to show. A lot of the homework is basically doing this sort of thing and doing this sort of thing, very, very, very handy trick. Really makes computing a lot of line integrals easier if you can show that one is conservative.